Hello students, so let us do a problem related to the related to the equation connected to the equilibrium constant and EM of the cell. That equation that we derived in the previous class. So let us do the problem. A standard electrode potential of a cell in which the following reaction, cell reaction they have given, it is 2Fe2 plus in presence of I minus iodide ion to gives 2Fe3 plus I2 plus I2. So this is the case where Fe2 plus ion Fe3 plus converting into Fe2 plus. So oxidation for iodide ion and reduction for ferric ion, Fe3 plus ion reduced to Fe2 plus. Okay, so this is the equation that they are given, cell reaction, and the standard electrode potential is given E0 cell, which is equal to 0.2236 volt. 236 volt at 298 Kelvin. Calculate the standard Gibbs free energy change. Second one, equilibrium constant of the cell reaction. So that's the question. Okay, cell reaction given, standard EMF also given. So let us calculate. Here now we know how to find the standard Gibbs free energy change. Delta G0 is equal to minus N of E0 cell. This is the equation. So E0 cell we already have, F we already know. So what is N that we need to find? Here now remember, don't confuse, Fe3 plus is converting into Fe2 plus, but 2 moles is there. 2 moles of Fe3 plus converting into 2 moles of Fe2 plus means 2 into 1. So number of electron involved is equal to N is equal to 2. So don't confuse with that. Always know, find the number of electrons involved in the redox reaction correctly. So here N is equal to 2 means delta G0 is equal to minus 2 into 96500 into 0.236. Apply here, you will get the delta G0 value, that is now coming around minus 45548 joule per mole. So that's an answer you will get for the standard Gibbs energy change. That's the first part. Second part, find the equilibrium constant. So we already derived the equation for finding the equilibrium constant, which is connecting the EMF of the cell and the equilibrium constant, which is equal to 0.0591 divided by N log K, where K is the equilibrium constant. So we want to find equilibrium constant means log K will be equal to N into cross multiply N into E0 cell divided by 0.0591. So 2 into E0 cell we have 0.236 divided by 0.0591. Apply here, you will get log K. Once you get log K, you can find the equilibrium constant, that is K, by taking the anti-log. So you will get a value which is around 9.61 into 10 raised to 7. That is the value for equilibrium constant. So after finding log K, you have to take anti-log to obtain the equilibrium constant. So that's no problem, that's related to the EMF of the cell and equilibrium constant. So such problems are there, you can practice yourself. Two equation, delta G0 is equal to minus NF E0 cell and E0 cell, which is equal to 0.0591 divided by N log K. Let us move to the next part, concentration cell. Concentration cell. So what do you mean by a concentration cell? Here now, generally when you talk about electrode, up to now we studied about a galvanic cell in a cell which one particular electrode having a particular standard electrode potential, another electrode having another different standard electrode potential. So difference in electrode potential between the anode and cathode is a driving force for the generation of electricity. But here interestingly we actually considering two same electrode means no, we do not expect electricity to generate. But here we actually what we are varying, we varying the concentration of electrode or concentration of electrolyte. That is the driving force here for the generation of electricity. So EMF can be generated by varying the concentration of electrode or electrolyte. So such cells we will call concentration cell. So as the name suggests, no, concentration cell can be two types, that we will say electrode concentration cell, electrode concentration cell, and electrolyte concentration cell, electrolyte concentration cell. As the name suggests, in an electrode concentration cell, definitely the concentration now that varies is the electrode concentration, and in the electrolyte, now the difference in electrolyte is the driving force for the generation of electricity. So let us start with the electrode concentration cell. So in the electrode concentration cell, we mainly talking about gas electrodes and amalgams, where metal with a different concentration. Generally, we taking the concentration of metal as a unity. So there is no point of changing the concentration of metals here. So what we are in electrode concentration cell, we are discussing about the gas electrodes. Gas electrode, you can imagine gas at a different pressure. So that now makes a difference, right? One gas electrode at a particular pressure and another gas electrode at a particular pressure means, yes, it's electrode concentration cell. And amalgam, you can think amalgam means a metal mercury combination. So there you can vary the concentration of these electrodes. So there we now let us start with the gas electrode, our famous hydrogen electrode. We can start. Now here you just imagine, here this is the case where now this is the type of cell that we are talking about now, electrode concentration cell without transference. Electrode concentration cell, concentration cell without transference. These two types, concentration cell with transference and concentration cell without transference. Such words we will see. What does it mean? Without transfer. Here, there won't be a direct transfer of electrolytes between the two electrodes. So that we will call without transference. If the ions are exchanged between the two electrodes, direct transfer of electrolytes takes place between two electrodes, then we can say that is a electrode or electrolyte concentration with transference. So that's a different, we will discuss more about that in the next session. So what does it mean electrode concentration cell without transference? Which means there is no direct transfer of electrolyte between the electrodes. Still the electricity is generating because of the difference in concentration of electrodes. So let us start with the hydrogen electrode. So let me think a platinum needed because it's a gas electrode. So hydrogen at a pressure, let it be P1 bar. Let P1 bar be the pressure, and which is dipped in a common solution, that is HCl, with having a concentration C, and another electrode, that we can say hydrogen gas at the pressure P2 bar, and another inert gas electrode is required. So here we considering P1 is greater than P2, P1 is greater than P2. That means pressure of hydrogen electrode at the cathode it is less. So P1 is we taking as higher concentration, high pressure, and P2 is the low pressure. So let us think, what type of cell this is. Here, you have to imagine a two hydrogen gas electrode which is dipped in a common solution, that is HCl, which having a concentration C. Okay, sorry, not C, yeah, C, concentration of the electrolyte is C, and pressure. What's the change here? Here, hydrogen gas, is taken, is maintained at a pressure P1 bar, and here another hydrogen electrode, which maintained at a pressure P2 bar. So that's only difference in pressure of the two gas electrode, which is generating a EMF. So let us now think about the anode and cathode reaction. Anode reaction, definitely anode means always release of electrons. So hydrogen gas is with the pressure, hydrogen gas with the pressure P1 bar is converting into H plus ion, to H plus ion, aqueous plus 2 electrons. So this is anode reaction for you, where release of electron takes place. Now cathode, what will be happen at cathode? The reverse, 2H plus 2 electron gives hydrogen gas P2 bar. So this is the anode and cathode reaction respectively. Anode and cathode reaction. Now let us imagine what's happening here. Here, hydrogen gas converting to 2H plus ion, and 2H plus ion converting to hydrogen gas. So overall reaction you can consider. Remember here both aqueous C. So here what will cancel? Electron will cancel, and H plus ion will cancel, because both are coming in the equation. So overall reaction will be H2 gas P1 bar is actually that's only in the left hand side, left hand electrode, and right hand side you will see H2 gas P2 bar. Everything else is cancelled. So H1 bar P1 is just like converter into H2 gas P2 bar. So this is the basic flow of electron you will observe. Electron are flowing from the P1 bar, the electrode of anode to cathode, where the anode pressure is P1, cathode pressure is P2. We have taken pressure of P1 is higher than P2. So that is the driving force for the generation of electricity. So let us have a newest equation for this. For this particular electrode, let us write the newest equation. So this is definitely a cell. Okay. Since even though both are same electrode, same gas electrode, same electrolyte, but the difference in concentration of the difference in pressure of the two electrode actually generate the electricity. So let us have an equation for E cell. We're talking about cell potential of this particular cell will be E0 cell minus 0.0591 divided by N log here concentration of the product divided by concentration of the reactant side. So take on the right hand electrode divided by left hand electrode. So it will be H2. So H2 gas P2 means you only need to consider the concentration here. So pressure at P2 divided by P1. So that will be the equation for the EMF of the cell, where P2 is the pressure of the gas at the cathode and P1 is the pressure of the gas at the anode. So we know for a hydrogen electrode E0 cell standard electrode potential for hydrogen gas E0. So E0 cell will be equal to 0. So let us apply that. So it will be E cell which is equal to 0 minus, that means minus 0.0591 divided by N will be equal to 2. 2 electrons are involved. So 2 divided by log P2 divided by P1. So that's equation that you can have. Now you can, if you want, you can change the now minus sign by now reversing the P1 and P2. So let us write the final equation for E cell, which is equal to 0.0591 divided by 2. I changed the minus sign, but now then you have to change this P1 by P2. So this will be the general equation that you can remember for a electrode concentration cell uh, with a different concentration of electrodes at anode and cathode respectively. We make sure the temperature we made constant because we doesn't want the temperature to influence the cell reaction. So 0.0591 divided by 2 log P1 by P2, that's the final equation for you at 298 Kelvin. Okay, so generally you can apply this equation where now remember P1 is the pressure of the gas electrode at anode, P2 is the pressure of the gas electrode at cathode. So that's the general equation that you can remember. So this is the case where gas electrode we discuss. Now let us discuss another type of electrode concentration cell, and now this time it's a mercury electrode. Sorry, it's a amalgam electrode. So let us represent the cell first. It is HgZn HgZnA1 in a common solution of zinc sulfate, that is aqueous A, which is now dipped in HgZnA2. So this is now we can represent another electrode concentration cell where A1 is greater than A2. So what's the difference here? Now two electrode, two amalgam where mercury is zinc. Zinc is the metal here. So zinc mercury combinations which is dipped in a common solution, that is zinc sulfate, where the difference is here concentration of the first electrode is A1, concentration of the another electrode, that is A2. That's the only difference. So let us first discuss the anode and cathode reactions. Anode definitely anode where oxidation always takes place. A1 gives Zn2 plus Hg plus 2 electron. This is anode reaction for you, where release of electron takes place. And cathode, just note the concentration, Zn2 plus aqueous A. So here HgZnA1. So cathode it will be HgZnA2 plus 2 electron gives Zn here here cathode reaction will be reduction. So Zn2 plus aqueous A plus 2 electron gives HgZnA2. This will be the cathode reaction. So overall reaction Zn2 plus will cancel, electron will be cancelled. So overall reaction will be HgZnA1 gives HgZnA2. So this is the overall reaction that you can write. HgZnA1 gives HgZnA2. So now let us derive an expression for the cell potential. So let us write cell potential as ER. Let us derive first. E cell is equal to E cathode minus E anode. That's our normal equation, right? E cathode minus E anode. So here cathode will be that and anode will be this. So let us find E cell is equal to E0 cathode minus 0.0591 divided by n log A2 divided by concentration of electrolyte, that is A. minus 0.0591 divided by n log A1 divided by A1 divided by A. This is the general way you can write. Now E cell is equal to E0 cell is there. So E0 cell minus 0.0591 divided by n log A2 by A minus E0 cell minus 0.059. Yes, minus 0.0591 divided by n log A1 by A2. So E cathode minus E anode. So here you can see E0 cell minus it will cancel. So what is rest? What is remaining? Here minus of minus become plus, and you have this will remain, right? So E cell will be equal to, this part is positive, so 0.059 divided by n log A1 by A minus 0.0591 divided by n log A2 by A. So this is just like 0.0591 divided by n will be, you can take outside, log A2 by A minus log log A1 by A minus log A2 by A, log A minus log B, log A by B. So A1 by A divided by A2 by A will cancel, so what is remaining is A1 by A2 log E cell, which is equal to 0.059 divided by n log A1 by A2. So that is a general equation that you can now think when now in a zinc mercury electrode, where now one of the electrode having a concentration A1, another electrode having a concentration A2. So now all you need, A1 is greater than A2, so always now you get E cell is positive, because now concentration of anode, concentration of A1 is greater. So E cell will be equal to E0.05991 divided by n log A1 by A2. So that is the equation for the cell potential of electrode concentration. So that's all about electrode concentration cell. So in the next class we can discuss what is electrolyte concentration cell. Okay. Thanks for listening. Let us wind up.